So, hello again. I'm back today, and today what should I say? I don't know. Um, there is a lot of things I want to learn and understand too much, but today I just don't know. I don't feel to show anything interesting, really. But let's see what we got today. I'm still thinking what to show. Hmm. So let me see. Uh, Okay, I want to talk about scattering today. That is what is coming in my mind right now, even though if I don't know. And by scattering, I mean scattering in quantum mechanics. But before that, if I will talk about classically what is scattering, how would we see scattering in on a large scale? If we don't want to zoom in too much, if we don't, uh, if we are safe from all those tiny subtleties in that small world, whatever is happening there, from a large scale what happens. So I will first assume symmetry means this is the point, this is my point of interest. From wherever you see this point, it the force almost feels exactly the same. So it has a, what do we call in physics, radial symmetry. It can be repulsive, it can be attractive, I don't know, it can be anything you want, but whatever it is only radially dependent. That's it. Some potential we offer, and if you want the force, you can just do this, you get the force. So what about this? So suppose there is this axis, and I just send some particle here with some initial speed v from far away, something like this. And what would it do? What would this particle do? So let me draw it very properly. What this particle will do is something like this, right? This is what it will do. So it will do something like this. I don't know, it can do anything depending on the force. It may go like this, it may just go like this. There are a lot of different possibilities, but whatever possibility it is, I know for sure that if it is a central force, the net potential, I mean the net energy of this particle must be like this. So there is this very nice formula. Am I writing it right? Plus, no, I'm not writing this right. I think I am writing this right. So this is what the formula looks like. I should recheck it, I guess. No, no need. So, why did I write this down? So the thing is, if the particle has even a little angular momentum, if it gets close enough, this full term just explodes. And since the energy is constant, these two get small, and this dominates, and it tries to just rotate around and escape from that force, whatever is pulling or pushing it, and it just shoots off, or maybe does something else, I don't know. But it will just it will have some kind of tangential speed. The closer it gets, the higher tangential speed it will have, something like that. So, and now, depending on what force it is, you can say predict what all possible trajectories there can be. One very common uh, uh, potential which you will generally see in standard physics textbooks. Almost I think every beginner's physics textbook, every bachelor's physics textbook, whatever book, it is always a 1 by r dependence potential, like gravity, electrostatics, yeah, mostly these two. And so, and you have a very nice effective potential curve for this. So these two together constitute an effective potential, and it looks something like this. And depending on what the angular momentum is, it the shape might vary, but overall what it looks something like this. And this plot teaches a lot. So this is my reference energy 0. Anything below this is a ellipse, anything above this is a hyperbola, anything at this is a parabola. That's it, that's all you have to know. And so let's say I have a 1 by r dependence and I want to see what happens to my particle if so let's say this is my center. I sent it here, let's say it's repulsive and it just went off. So every instant my this this particle was pushing my other particle, and it kept getting pushed and it just flied off. And you can use this to actually see the effect. So it had some energy something like this, and uh, so it had some energy like this, and this is the energy, what should I say, bar, energy bar you may say. And so so this energy bar just tells you that if it is bounded or not, like will it keep rotating around it, orbiting around it, or it will just fly off. If it has touched 2 points something like this, then it is just stuck inside, then it will keep orbiting or do any kind of wacky stuff around it, it will keep repeating. But you can see it's only 1 point, nowhere else it touches, it just keeps going. And now I have to suppose I know my force. Suppose the force is the potential is some constant divided by r, or if you want to write it in terms of force, it will be 1 by r square, k by r square. And the question is, what will happen if I also there is something called impact parameter. So the question is simple: if I shoot it perfectly parallel direction towards this center with some speed, with some kinetic energy, with some speed, what angle will this make? What angle? So let's say after some sufficiently long time it went off somewhere here. Now if I take see the angle of this speed vector, so almost the speed will be same here and here, far enough, because at the higher distances there will be no influence of potential, and all the potential energy gets converted to kinetic energy, blah blah blah. Whatever speed you had, you have the same speed but direction different. So what angle will this make? That's the question, that's the all question there is. Give me a relationship between the impact parameter and angle, give me a good relationship for that. That requires a lot of skill, I think, like seriously I don't know how to do it, I don't remember. I want to do it now. So what can I do? Of course I will conserve the angular momentum, that is one of my best things I have, that is the most important thing, I guess. I can't do anything else, right? I know the energy, I know the angular momentum, of course, since I know this, where my point is. And so scattering sometimes messes my head. what can I do? This is a hyperbola, right? It will always be a hyperbola if it is repulsive, or would it? Right now, it is safe to assume it is a hyperbola. You can have many other trajectories here. You may be going a little closer than you were supposed to, and you might do something like this as well. All are equally valid, but I have to find out, okay, fine, but what angle will be made in this scattering? This is gonna take a whole day if I sit, but I think it will be worth it. I want to do it now. So this might, so if this video becomes, I don't know, 1 hour, 2 hours long, you can just leave or keep skipping to see what, or watch it 2x or whatever you want to do. So now, hmm, I think today it will just end in classical scattering. Next video will be on quantum scattering. Today was just classical scattering. So what will happen now? There are a lot of formulas there. Of course, I can just check on a book, but I don't want to do that. I want to see how good am I recalling, or did I just memorize it all along? Did I? Well, everything I've learned in some sense is memorization. But how good of learning this memorization is depends on how much I just spend time on giving thoughts on it, right? What is good learning? It is just memorization with some extra thoughts sprinkled on them, some time given to also think, than just blindly shoving in your head, right? Is that what all learning is? Uh, I have so plain views on everything. So okay, let's keep. First, let's see what happens. Hmm. Now, what can I do? What can I do? What can I do? What can I do? How will I find what angle is made? That's a good question. Suppose there was no potential at all, then I know for sure this is what is supposed to be happening. If the potential was very strong, here itself I would have seen the curvature, right? So, a lot of things. What can I do? I know for sure what will be the closest distance from here. I can calculate that easily using math. All this math I can use and find the closest distance. But if I find the closest distance, I don't know how will it be useful, right? Okay, let us find the closest distance first, and then I will think. I don't know. It might be helpful. It might not be helpful. I'm just wandering around without any purpose. So let's see what will be the closest distance. So for a beginning, if I assume that the initial speed was somewhat v, then kinetic energy is half mv square, initial speed. And okay, I want, let me use u. Should I use u or should I use v? I think I will use u, because I generally use this alphabet for initial speeds. V. Okay, so u, it has some speed half mv square. And now if I use this formula, this is my energy, right? This is my total energy. If because from far I am coming, there I had no potential there, so yeah, this is my initial energy. So half mu square equals half m. I don't know what r dot square will be, but later we will think about it later. I know the angular momentum, the angle it's making per unit area, right? So the angle it's making per unit area, I know it. So uh, it will just be, I have to just know, sorry, area it's making per unit time, this area at every instant it's just sweeping this area with respect to the origin. You can just do the math, like for example, let me say, let's suppose the particle was here, then it will come here. I mean, oops, what am I doing? Suppose the particle was somewhere here, then it came somewhere here. this area I am interested in, and it is just the rate of change of area of how should I say, let me just show you. So I can show you algebraically, but geometrically if I want to show, can I show it? Let me try geometrically. Suppose this was uh, the right angle triangle which was swept, right? So after some time what happens, the particle comes somewhere here, and this is the new right angle triangle. So how much extra area was cut? This was the area, right? This is all the change in area. And what is angular momentum? It is just proportional to rate of change of area with respect to my point initially away from wherever I am measuring it, and this is the area which changed per unit time. You know how much time there is, you know how much everything. So this area is approximately equal to uh, m no, what am I doing, the speed times no, first let me write this distance, right? This distance, let's say delta x times the time taken times the height, of course, which is b in my case. And so this will be uh, so delta x, why did I use t? No time, no time. This is a delta x. Area is um, length times breadth, and this is u times delta t times b. This is my small area made. So my rate of change of area, I just send this time here, is ut ub, and angular momentum is proportional to rate of change of area with respect to time, with respect to that point I am measuring the angular momentum from. So and what more do I have? Let me recall it. What was this? Angular momentum is mv times r, and I can just multiply 2 and 2, and this is area, right? A small triangle made. This is r, this is v, r times v by 2, because half into base into height, r square. Yep. So this is, so my angular momentum will be 2m times dA by dt, and so it's just 2m ub. This is my angular momentum. I hope I did it right. Let me just see it for a circle. This is a circle. The angular momentum is m v r, and the area it sweeps every instant, I can also calculate that. This will be equal to, wait, m, so v r, m times dr by dt times r, uh, mhm. Oh, I should not write r here. Arc length is getting covered, so let me just write s, ds by dt. And now so if I just multiply it with half, multiply and divide by 2, this term will just give me area being set every second. So this is 2m times m by, what is it, half times ds by dt times r, and this is 2m dA by dt. Okay, I guess everything feels good. If you don't still trust me, then you can also do this. So since circular motion is linear, you just take area by time. This will be equal to dA by dt, right? And this is equal to pi r square, and the full time taken you can easily calculate. That will be ds by so you know that ds by dt times uh, the time taken to complete one full revolution will be 2 pi r. So t is 2 pi r by ds by dt, and you just crunch all the numbers here, pi r square, just to do the arithmetic, by 2 pi r ds by dt, cut, and a by t, this is your da by dt. So you can clearly see that r by 2 ds by dt is your da by dt, and you just send the 2 here, r ds by dt is 2 da by dt, and you just sprinkle a little what do I say, filler here, the mass. So you have this full term. This thing is nothing but your angular momentum, and that's 2. uh, so this is good. Angular momentum is this. So where was I have to come back to what I was doing. I was finding the closest distance from the uh, closest distance from what, yeah, from my particle. So let's say the mass of this is m, the mass of this is m. So yeah, this is approaching with some speed u, right? That's what we assumed. So I can write now 2mub, 2mub, right? 2mub, uh, 2mub, and then oh, L square by 2m, right? L square, so this is just L square by 2m, and 1 by closest distance square, and then plus other distance, I know it is a k by r square, sorry, k by r. And so now what more can I do? I know this, so let me just write this as initial kinetic energy E. uh, so E equals half m r dot square plus, so what will happen if I do the math here, 4 m square u square p square. Okay, the angular momentum is 2mab, 2m times da by dt, which is just uh, u times p, 4m square u square b square by 2m, and then 1 by r square plus k by r. As you know, I need the closest distance in terms of the impact parameter. That is the relation I am trying to find out. So this much is correct. What more can I do? So now this term, if I multiply 2 on both sides, this, also u square on both sides, this will be my initial kinetic energy, right? But why would I want to make things more complicated? I won't do that. This is just power of overthinking. Yeah, this is my kinetic energy. What was I thinking? E equals half m r dot square plus 4e b square, wait, yeah, by r square. I have this r square, so dimensions are still preserved, nice, divided plus k by r. And let me use a variable, different variable, so that it is the closest distance I'm talking about. It should, So I will use the alphabet I J K L M N O P Q C R S T U V W X Y. I think R is the only which okay, fine, let's just keep it. A special R which has a minimum distance from the. So still my job is not done yet. I have to look at this potential and see what more can I do. I have to find this point. This is my only objective. I have to find what this point is. This will be my closest distance. Closest distance. Hmm. How will I find my closest distance? No, no leads yet. So if I somehow hmm, if I somehow get rid of this, I am done. That's for sure. 4m square u square b square by 2m, and I just cut the m's, and half m u square, that's energy. Hmm. There is no way to get rid of this. Or is there? Hmm. Or what will be the radial speed at the closest approach? Look, if I assume that this is if on this argument, if the closest radial speed is 0 at this closest approach, I will be basically done. I will just get my relationship, but I'm not confident on that. I don't know what it will be. So I don't want to take any risk on it. So at the distance of closest approach, will this be 0? If yes, then geometrically I will be fascinated and also confused at the same time. Hmm. Am I forgetting anything else? Hmm. I think I can use some argument. Look here, as time is passing, what is happening here? This guy is trying to come closer and closer, but as time is passing, now here it's going to farther and farther. So this means at this sweet spot, it must neither go slower or faster. Damn, my explanation skills are so shit. I don't know. It is just my gut feeling saying that. I just explained my gut feeling. I don't have any rigorous proof for why it is the case. Uh, so now, so what should I do? What would I? How will I find this out? Is this zero? Is this not zero? Come on. My head feels like a tube light, broken tube light. I guess it's just twinkling. Hmm. What can I do? Hmm. If all only there was some nice, neat, clean argument that yeah, here it should be zero, I would have been very happy. But I don't have any solid argument. Here I can see like okay, as it is approaching, it will still keep doing, keep getting slowed down, and when once it comes here, it gets very slowed down and it just goes away. But it still that doesn't feel enough, right? You must have some notion, some idea what. I think this should be zero at the distance of closest approach, but I don't have any valid reasoning for that, which is eating me inside. Hmm. Hmm. So, in any central force orbit, the distance of closest approach will have The radial component 0, is it? Hmm. I think there is only one way to tell it. Okay, I have to murder the maths a little. I am murdering the maths. Get ready. E is equal to half m r dot square plus l square by 2m 1 by r square plus v of r. So at the distance of closest approach, uh, what happens is, hmm, let's say this is my distance of closest approach. Okay, at some time t this is my distance of closest approach. So what happens is, uh, how should I say, so at some time t naught I went to my distance of closest approach. If I just, so if I just fast time a little bit, what happens is, say that I I will definitely be more than my distance of closest approach. And if I reverse the time at that, or close to the distance of closest approach, it will be lesser than my distance of closest approach, because that's what distance of closest approach is, right? Either you will just stick together, or else you will get, you will fire and you will come close and then get far again, or vice versa, close far close. Distance of, is there anything called distance of highest approach? Yeah, there can be. In an ellipse you have both distance of closest and highest approach, and in both cases they are actually, the r dot is 0 at the endpoints. Okay, distance of closest or maximum, whatever. You see the sign changes here. So if I draw it as time passes, as a graph of time, when at time t plus delta t it was here, and at time uh, t minus delta t it was here, and it will keep happening, right? Doesn't matter how small t is, only at this some sweet spot, which should be your delta t going to 0. So at this sweet spot, by math, because if you have negative and somehow magically you become positive, and it is continuous, at some instant you must have crossed the axis, right? You some instant the value must have been 0. This is my logic. It might not be rigorous enough, but this is getting recorded. Anybody is free to point out why I am wrong, or give some better reasoning why this r dot is 0. I'm pretty sure there is some very nice and neat reason why this is 0, but right now we'll just stick with it. God knows how will I be a good physicist. So you have 4e b square. R square. I am just multiplying r square everywhere. Not r square won't be here anymore now if I multiply r square both sides of equations. If I just do that, plus kr, right? So, or I can write r square is equal to uh, 4b square plus k by er. Are the units matching? Distance squared, distance squared. Is this distance squared? Let me check. Energy is equal to constant by distance. The units of this constant are energy times distance. Energy times, yeah, everything is good. So I can have a quadratic equation r square minus k by e times r minus 4b square is equal to 0. So your r is, of course I need it positive, so uh, k by e plus or minus square root of b square, which is k by e whole square plus 4ac. 4 times 4 is already 16 b square by 2. And this thing should be greater than this thing, because k by e square is there and extra numbers are getting added, so I have to keep the plus term only, no other terms. So this will be k by e, I also multiplied fully by half, plus square root of k by e square plus 16b square. I don't know how did this 16 pop out of nowhere. There is nothing feels so natural or special about it. Only 3 4 5, mostly 3 or 4 comes in basic fundamental equations. So 3 2 or 4, so 1 always. So something fishy, something feels fishy. What wrong did I do? Hmm, honestly nothing feels wrong so far, so uh, I guess I am good. Hmm. Uh-huh. Hmm. So if my constant is 0, distance of closest approach will be, of course, I can just analyze, right? If my constant is 0, which means no potential at all, my logic logic will tell me distance of closest approach should be b. I definitely can't see b. It will be, according to this, it will be uh, 16 by 4 b square. That's 2b. No, 2b is not the correct answer. So somewhere math mistake is there. Hmm. Where is the math mistake? Energy is equal to 2 mub square. 2 mub is the right, I think 2 mub, there is nothing wrong in 2 mub. uh, or is there? Hmm. I think I have messed up a little here itself. Hmm. So the mess up, I guess, is mm, hmm. What is the mess up here? I'm just getting an extra factor of 2, I think, and I have to just fix it up. So you had a triangle like this, and after some time it just increased in something like this. Suppose a particle is going in this direction, so this is the direction of my particle's movement, and after some time it got this, and you are just for figuring out what this area is. I think it should be just MUB. Of course, angular momentum is correct that L is 2m dA by dt, but I think rate of change of area is just MUB by 2. I mean just UB by 2. That is what I am getting. But that's weird. Can I see it? UB by 2. How is this possible? Okay, the simple reason is my bad assumption. This is not the area I was supposed to be calculating. This is not the area I was supposed to be calculating. This was the area I was supposed to be calculating, because this is what angular momentum means in radial symmetry. Uh, well, if I am talking about angular momentum, I am interested in radial more than anything else. So yeah, so some math mistake, but yeah, this is the thing in physics. Look, if you did some mistake somewhere in the middle of derivation and all that, that's okay, you are human, that's why you did it. But if you can just once you get the result and you watch around, like, is there a mistake anywhere, did I mess up anywhere, you are fixing it, right? That is more than enough, I think. You don't need to be perfect, brilliant, and cry about doing some arithmetic mistakes up there. It happens, you can't do anything, you have nothing to prove anyone. So okay, in exam you may be in trouble, but anyway, other than that, I think it's not a concern. You should not be concerned. You should only focus on learning sincerely. That is all that matters at the end, I guess. So here you go. K by E plus square root of K by E whole square plus 2b square. This formula works, I think, because when k is 0, your impact parameter will be b, which is getting shown here. This is nice, this is correct. For any potential, this is the distance of closest approach. Okay, fine. Distance of closest approach, if you know the angular momentum, if you know uh, what should I say, speed, then the impact parameter, you can easily find the distance of, not easily, but definitely you can find the distance of closest approach. I will call this, I will say, let's say d. This is the distance of closest approach, d. And now, and also I found that there should be a 90-degree mate here, which reduces my work, I think. And so the thing is, an extra angle phi is being made here. So if I can somehow this is the tangent, and I think I can easily tell what the angular momentum here is. That is not an issue at all, right? I can find an relationship between a phi and my impact parameter. I will tell you how I will do that. So look here, if you know the phi, let's say you are some r distance away, and this, let's say you are some s distance, not s, I will use l distance away, I guess. So you know for sure that initially your rate of change of area, look, what does angular momentum say? Rate of change of area getting covered with respect to time won't change, it's just constant, and your mass is constant as well, don't worry, no mass decay. So you know that your angular momentum is m b u. And what is this? This is the perpendicular distance, and you know that at infinity, as you keep getting further and further, you will get your u back. Initially and at the end, both u's should be same. So I will exploit this m, and then you have this u. Now this perpendicular impact parameter, you so you will have this job will be done by this distance here. Wait, I think I am being too optimistic here. That might not be the case, I guess. Hmm. Okay. Distance of closest approach is depending on your force and energy. This makes sense. This formula, you see, the more the kinetic energy, you are very likely to get closer to your how should I say uh, target. And this formula, yeah, it's perfect. And the more the force, you are more likely to be away. Also, more the impact parameter, again you are likely to be away. So it's perfect. This formula is like I don't have any doubt in this. It's like best I can have. So no doubt in this. So now how will I find angular momentum after some other instant? That's a good question. Huh? Hmm. Hmm. What can I do? So I have some particle, and it is going in some arbitrary direction, and I want to find rate of change of area with respect to this guy. How would I do that? I can use a little vectors, I guess. Vectors will definitely help here. It will be a one shot. Okay, I am forced to use vectors here. But vectors beautifully might work well. So you know angular momentum is what is angular momentum? This is r cross p, and I know the momentum magnitude. That is more than enough for me. So r I don't know, right? So let me say it is some xi plus yj, right? Oh, also, yeah, let me just keep it this way. This will get cross product with uh, mu cos theta phi cap plus mu sin theta. K cap. Perfect. And then what can we do? Hmm. Also, I know my x and y. I am analyzing it all at a very large distance, of course. Uh, I don't know what can be done here. This is parallel. Let me draw a neater diagram. Then I will. So here, let me try to draw a neater diagram. So let's make this a straight line. This is not a straight line. Oops, I wanted a straight line here. Black color. Here we go, a straight line. We have a straight line. Then we have some particle here, and then we have something like this. Let me try again. You have some distance of closest approach here, distance of closest approach, which will make a 90 degree. And then at infinity this will make some angle theta, almost very highly close to. I will just take equal to. I'm tired of using approximations. I just know when to use, when not to. So, and if I just for reference draw a parallel line, I don't know why I'm doing this, but parallel line, is it necessary to draw or not draw? Hmm. Let's say particle is going here. Now what? So let me. I want to find this angle theta, right? That is all why we are doing all this. I know this distance of closest approach. I have calculated this. I know how fast my particle is coming initially. So now what can I do? Hmm, what can I do? That's a good question. Hmm. I can. What I can do? What can I do? What can I do? What can I do? Come on, do something. What will I draw perpendicular? Wherever I see, let me just draw perpendicular. I think this is a very bad practice I'm doing. I'm just, uh, blindly drawing perpendicular tangents, parallels wherever I see, which is, I don't think, a very good idea actually to solve any problem. Solving problem, I think, means to uh, find. I mean, being good in solving problem is, I think, the ability to get the ability to see uh, the how should I say, see the problem in the right direction, such that you get a very nice understandable answer. But if you are just trying every way possible, you are just increasing your time and all that, which is not a bad thing sometimes, because if you don't if you're not able to see it, is maybe it is not your fault. It's okay. But just think, just go back, and I mean, just step back a little and think for a while. If possible, you may get something. Of course, no, nothing is certain. Hmm. Hmm. What can I do? Come on. What can I do? The particle is somewhere here. Making some angle theta plus phi. And just going and going. Can I give any geometrical arguments which can reduce my job? If this is theta, then this should be theta. And if I draw a 90-degree here, then this should be some angle 90 minus theta. Of course, this is 90 minus theta too. And if this is 90 minus theta, uh, let me just remove this perpendicular which I drew. This feels too unintentional now. Uh, hmm. What can I do? What more can I do? Hmm. Even if this parallel line is looking nice, fancy, I think I should just rub it unless I get some good idea. Or let me keep it because this parallel line is giving me theta. Hmm. What will happen? What can I do? Nothing is clicking. Hmm. Hmm. Come on. Hmm. Some messages I got. Hmm. What can be done? I'm too much lost now. Hmm. Can I use this again? This relationship. Will this tell me something? but I don't know r dot square at the infinite. Hmm. Hmm. Can I argue that even at infinity, uh, r dot square should be 0? Hmm. Because at infinity, this will be as it is. This will be 0 anyway again. Okay, no, I can't say anything, I guess. I don't know how will this behave. Hmm. Oh, wait. I think at infinity, I know, like this will be my kinetic. Everything will be converted to this, and all of this will vanish. Yeah, that's true. That's what will happen. Yes, perfect. At infinity, this should approach to you. That is for sure, 100%. So if I know that, then at infinity, I will no have no angular complement. Everything will be because of this. And if that is the case, so then how will I balance the angular momentum? Hmm. Hmm. Let me write it again. Energy is half mr dot square plus L square by 2m 1 by r square plus V of r. In our case, let me just write this k of r, k by r. Hmm. Okay, I think this limit is not valid. My intuition said that, but I guess it is not. It will cause a lot of problems. Hmm. Then what can be done? At least I can be sure that if I draw a vector here and I draw a perpendicular here, and whatever the length, this length should be uh, b, and if this is phi, so I can say that, and this length is l, I can say that L sine phi must be equal to LB. That is just math. And if I somehow happen to find L, my job will be done. Can I find L as a function of theta? Hmm. So at large distances, my particle will travel ut after a long time, and if I use Pythagoras theorem, this will be b square, this will be equal to, this will be just equal to ut square at large distances, which will not give you anything. If I could give some geometrical arguments, it could have been better, I guess. I know the impact parameter. If I can somehow write theta in terms of phi, or phi in terms of theta, whatever, I think I am done. If I just find a relationship between them. As you can see, my distance of closest approach is this, and it depends on my impact parameter, of course. And hmm, impact parameter, come on, give me some hint, please. Hmm. How will I write angular momentum when it is parallel? R cross B, right? This is what I got. Hmm. 45 do this. This is theta. This is theta. So this angle must be 90 minus theta. If I find this angle, then what will I do then? What will be the point of that? Hmm. Hmm. least I can find this distance, which I don't know what I will do with, but I can. But that is also has a having a data dependence, which hmm. Hmm. What? Hmm. Honestly, it is very difficult, and I see there must be some new information introduced. Hmm. Uh-huh. What should I use? What more information? So if I somehow also find like what will be the angle made here, provided I know the distance of closest approach, will it be helpful? Well, I can do that. I guess, right? Yeah. Hmm. If I know my distance of closest approach for some parameter, then I must know uh, what more should I know. So I will know that all the energy here will be, so no r dot component, so all the energy here will be uh, kinetic energy, sorry, not regular, kinetic energy of angular part plus potential part, right? I will know the speed here, and then since I also know the angular momentum, hmm, hmm, since I know the angular momentum, then what? I will just know the only thing I will found is just the speed. Fine, just the speed again. What will be that tangential speed? I can easily find, but I don't see it relevant here. Like what will I do with it? Hmm. I think I have been silent for a long time. I'm just staring here, not able to find anything. No clues, no idea. Just hitting my head. Hmm. What to do? It will get closer or it will get farther. What will you do? Please, somebody help me out. Uh, going silent for so long. Video is just running. It's better if nobody watches this other than me. Hmm. What can be done? Hmm. Hmm. Impact parameter. Come on, please give me its fight. Tell me the right way. Show me the right path. I at least can see that the particle which was initially moving parallelly with respect to my axis is now making some angle alpha here, and this alpha will keep increasing a little bit, slightly increase a little more until it finally reaches a saturated value, and that saturated value is what I am behind, what I'm after. What will be that saturated value? Suppose x is my distance away from the away from my center core towards which my particle was running. This will become x almost, this will be x, this will be x, very large x, and this will have I don't know what value this will take. I know this value. Hmm. It is way difficult than I thought, really. It makes me feel like I'm a joke. Maybe I am. I second on this, but I will not give up. This is all I know. This is all I do. Let me use some other variable because it is taken less angular momentum. Hmm. Hmm. If I can exploit the geometry of a hyperbola, maybe I will stand a chance. I think. Like this is an hyperbola, right? Symmetry. This is your hyperbola, and this asymptotically speaking, these two will just make equal distances from your far infinity point, and 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 I don't know what next. Yeah, this is my core, and okay, I think I was wrong here. I mean, I was very stupid here. At far infinity, this angle won't make any sense anymore. What was I thinking? It will be just zero. Then how will I find my angle? Hmm. I have to rely on my geometry. That is all can be said now. I have to rely on my geometry. Only geometry will help me out here. Hmm. So here, if no angle is being made, suddenly, so what angle will be made depends on the bendiness, like stretchiness of my hyperbola, right? I can have all different kinds of angles. So if I somehow figure out the stretchiness of my hyperbola here, then I think I have a chance here. I can tell uh, what angle is being made. So let me erase this. I think this is not needed anymore. This was, I think, a very big distraction. If I draw a parallel towards this velocity vector, does this angle mean anything? It's really weird, like hyperbola, this is so symmetric and still this is giving me so much troubles. Hmm. 90 degrees, 90 degree, 90 degree, 90 degree, 90 degree. Hmm. I am not interested in this alpha, is it? Let me rethink the problem. So rethinking is apparently a healthy habit. You don't need to stay stuck with whatever you had. It's okay. It just goes. Hmm. So now, if I whatever vector velocity vector is this is making, if I make the same vector here in this direction, what angle this is. Let me just extend this. Hmm. I have to find out angles made by hyperbolas, how they are determined, I think. Hmm. Well, it is just a matter of like their slopes is asymptotically, right? Whatever slope this asymptote will make, that will be the angle. So I think the problem boils down to if I can figure out what angle. Okay, this is really messy. Remove this all. If I can find out, first of all, what angle is being made here with respect to this, of course. With respect to uh, with respect to this, what angle is being made, and then just add this angle. Maybe I am done. Again, this is a new preposition. I don't know if this is valid or not. I know the distance of closest approach. If I do know the distance of closest approach, I know what kind of hyperbola this is. Can I find what the angle will be? Hmm. 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 What should I do? If I rotate this. Hmm. Things are very. Hmm. What will happen if I take a vector which is not radially outwards and rotate it with some angle theta? Hmm. Well, I will have difference of these vectors which are rotated. Right. And the angle between these two vectors will be preserved still regardless. So it it is safe to say that it will make an angle theta. Yes, correct. Yeah, I think yeah, this should work. If I find these two angles and just add them, that is my theta. So this, let's say this is my angle 1 phi, and this my other angle, which is I don't know. What should I write? Psi, let's say. If I find these two angles and just add them up, I am done. I wouldn't be wanting to do anything more. So how will I find each of this? Let's see. This is the easiest one. Since I know okay, I regret saying this is the easiest one, but I think this can be found. Hmm. I know the distance of closest approach, and I know the impact parameter. So, hmm. So what would this be? What would this angle give me? Uh, Let me clear some notifications. What would this angle? How will I find this? Hmm. Hmm. So now, let me see this equation if I get some idea. If this becomes 0 at closest approach, you know your angular momentum, you know your distance. I have to find the nature of this hyperbola. Only then I think something will happen. Hmm. And if I'm not wrong, no, maybe I may be wrong. So I won't comment. Hmm. Hmm. if I if there is a requirement to explicitly solve this and substitute, then I am dead. It will be total hell. I don't want to do that. Just geometry, come on, some geometry. Hmm. Hmm. Some geometry. So, okay, if this is 5, this should also be 5. What will I do with it? Something clicked, I don't know. So if I made this as my reference, particle is coming from some angle and going back at the same angle. That is all I can see now, right? Hmm. That's all I can see now. And hmm, if that is the case, hmm, if that is the case, my vector was something like this initially, but I did some rotation. I did some rotation. I don't know what kind of rotation I did, but I just converted everything to this, right? So, in a sense, this angle matters. Hmm. Hmm. Asymptotically speaking. So, what was I doing again? This particle is coming like this, and I tried to analyze it like this. So, something was like this, and I converted to like this, right? This got converted into this. A rotation was made. And how much rotation? It was, I think, this much rotation. I don't know what angle this is. Yeah, so if I can somehow find this angle, I may get somewhere. Hmm. and that very angle should be this, I suppose. Hmm. So if I can somehow figure out the property of this hyperboloid, I can tell this angle, something like the eccentricity or things like that. And yeah, I have to. Am I right here? Files. Yeah, I think these two are the same files. Hmm. Hmm. Once I do that, I have to also find this angle. Or is there just one angle all along and I'm just overdoing it? What if it is just these two are the same angle? What if this is the case? Hmm. Regardless, I have to come back to understanding how are angles related in a hyperboloid trajectory. If I can do that, then I may reach somewhere. So, what is the eccentricity of a hyperboloid? So, how do we find what is eccentricity? I think it is something like C by A, I guess. If this is 0, I have a circle. If this is 1, I have parabola. And if this is between 0 and 1, I have an ellipse. And if it is greater than 1, I have what do we say, hyperbola, right? Hmm. If I think it this way, then it will be over. I will never be able to do anything. Let me think in terms of equation. X square minus a square plus y square minus b square is 1. This is an ellipse, and if I do this, it is a hyperbola. And how will this look like? When I put y equals 0, I will be a distance away, and here as well. And when I put x equals 0, then I will not get anything. Hmm. So it will be something like this. I am not interested in this kind of shape. I am more interested in this shape. So I think the right figure I should be looking for is y square by a square. Y square by, let's say, whatever is below this, b square, I guess, minus x square by a square is equal to 1. And since a and b have b since b has already its job assigned, I will use like p square q square, I guess. These are just numbers, right? And you can do the calculation. This kind of trajectory as the slope of this is asymptotically going to be somewhere, going to go somewhere. So 2 times 2 times by dy by dx into 1 by p square plus 2 times x minus 2 times x by q square is equal to 0, and 2 just gets cut, and you get dy by dx is equal to uh, dy by dx equals at any point x by y times p square by q square. I don't think this will work. So here I can clearly see that y square is 1 plus x square by q square times p square times p square and this I can write as so I can write y square is just p square plus x square p square by q square, and this I can write as x square times p square by q square, p square by x square plus p square by q square y square. So implies that y must be equal to x times square root of p by x plus p square by q square. This implies that as x is very large, slope must be equal to uh, p by q. Hmm. P by q. P by q. If I can somehow find the equation of hyperbola here, I can at least come up with some good idea. So what all do I need to uniquely determine a hyperbola? Well, I need distance of closest approach, and what more do I need? I just need two numbers, that is for sure. If I look here, I can clearly see that angular momentum and energy are more than enough to uniquely determine a hyperbola, and I know both energy and angular momentum. So I must be able to uniquely determine a hyperbola if I know these two. But how will that look in my param in as how will they look as curves? That I really don't know. That is also a trouble in itself, honestly. So you may say that I have reached nowhere for the next 2 hours, even after doing all the something. Maybe should I give another hour? I don't know. this is my particle, distance of closest approach. It will look something like this. So this is what the diagram is telling me, something like this diagram. Hmm. Foci is somewhere here. I can't find the foci here. Will this be my foci? I don't know. Hmm. Physics is difficult now. I think about it. Too many things to learn. Hmm. So now what to do? I tried a lot of stuff. I don't know, went through so many things in my head to try to solve this, but I think I reached nowhere so far. Hmm. Hmm. What to do? Hmm. So angular momentum and energy and total energy and angular momentum will uniquely determine the shape of my curve. This is for sure. In of course this potential, but what will it be? I don't know. Of course there are these formula for eccentricity which I don't remember. If I do, I think my work will be easier. But I have to solve all the differential equations for me to find that eccentricity to have any meaning about it at all, which I really don't want to do. I just want to. Right now, I was just thinking to give geometrical arguments to solve this, but apparently, without solving this differential equation and finding an explicit relationship between r and theta, I don't see us going anywhere. That is the, I think, sad truth. Hmm. this much I think I am sure, more the angular momentum, more will be my curve, my path, the trajectory curve, bending will be more if I have more angular momentum. And distance of closest approach will be determined by my energy. Like more the energy, lesser the distance of closest approach. These two things I think I can tell. Other than that, without explicitly solving, um, it will be very difficult, I think. Hmm. So I still want to solve this, but it is just getting scarier and scarier. Let me try to find R and theta dependence and then try to do something. I think I have to go through the dirty thing. I didn't expect I will do this, but I have to do it now. Uh, I think it will be. I have a classical mechanics textbook somewhere here. I think if I take that, there will be the relationship of that. But what point will it be if I do it by seeing? So here I go, going through all that pain for no reason. I think I just want to stop it here. This is one of it. Let me just keep it some potential V of r. Okay, no, no. Anyway, we can do this. For any general V of r, I have known. And of course, this is what will this be? Will it always be just r? I think so. Hmm. And then what will be r theta dependence? Hmm. Okay, I also wrote the angular momentum formula. Hmm. So. Hmm. think I will not be able to do this as well. Mm, mm. Even this is very difficult. Mm. Mm. I guess I have to go back. I will come back in the next video continuing this. It was, I don't know, it's depressing. I was not able to get anywhere. But bye.